Hi everyone, this is Dr. S. Today's lecture, chapters 10 and 11 on chemical reactions and solutions. As you can see, will be done asynchronously as we all voted on a week or two ago. And I will be keeping this video on YouTube for future reference. So by all means, you can pause, you can come back and revisit if there are any bits that are still confusing to you. And of course, if that doesn't clarify things, by all means, reach out to me and we can set up an office hours appointment to clarify, or just find me during lab. Okay, the core concepts and learning goals for today's lectures are the 4 items. The first thing that you should be able to do by the end of the lecture is to recognize the ionic or covalent nature of a molecule based off its molecular structure. And to that end, once you have a feel for the relationship between a compound's formula to its molecular structure, we can use that to really understand and identify the basic reaction mechanisms that we can expect for, in a chemical equation. These are going to cover the first half of the lecture. The second half of the lecture, which really concerns solutions of compounds, really is going to be understand how ionic versus covalent molecules would behave in a solution, because they won't behave identically, and also being able to predict the changes that a solution would experience depending on what is dissolved into it. Okay, so let's get into the meat of this. In the last lecture, we ended off introducing the concept of ionic versus molecular compounds, or ionic bonds versus covalent or molecular bonds. And to just really briefly recap, an ionic compound, which is also known as a salt, let me just turn on my pen here. So ionic compound, also known aka salts. These are formed when a metal element and a non-metal element ionize each other. So if you recall something like chlorine, it's going to have 1, 2, 3, 4, 5, 6, 7 reactive electrons in that outermost valence shell. And a metal like sodium, it's going to have 1. All right? And because we want the octet rule to come into play, where everything needs to have basically 0 or 8 electrons in its outermost shell, that chlorine is going to, oops, I forgot to draw that 7th one. It's going to steal that electron, okay? And it's going to make this a non-metal ion, and it's going to make this a metal ion, positively charged, negatively charged. We gain a negative electron, and we lose a negative electron, hence the positive charge. And consequently, when we do this, we're going to form sodium chloride salt, NaCl, solid, like this. And that electrostatic attraction between these two entities, that is the ionic bond, okay? Now, this is a bit of a simplistic picture. Something to know about ionic compounds is that they do not have, they lack a discrete unit or molecule. So a better way to really look at this is in this picture over here. So this is like a cartoon model of a sodium chloride salt. And the chlorides are these green balls, the bigger ones, and the sodium is the smaller purple ones. And it's sodium, it's chloride, sodium, and it repeats, okay? So the ratio of sodium to chloride is 1 to 1, but there is no like sodium chloride molecule. It is a lattice that goes on, indefinitely, as big as the crystal exists. And if you look, this is like an electron micrograph from like an electron microscope, this picture. Oops. All right. And this is one salt crystal. This is one molecule, so to speak. Salts don't really have molecules per se, they have crystals. But this is, one network of sodium chlorides bound together. All right, so when we write down the formulas for ionic compounds, what we're really doing is we're using something called the empirical formula, all right, which is not a true molecular formula in the sense that a salt doesn't have one sodium and one chloride, but rather it has one sodium for every chloride. It just shows the ratio between the two. Calcium chloride is going to be one calcium for every two chlorides, all right? And that's because calcium has two reactive electrons, and it can give one of these to each a chloride, okay? Covalent compounds, this is probably what you really think of when you think of molecular formulas. So to rehash, covalent compounds, that's usually comprised of only non-metal elements, okay? So like in this molecule down here, where's my cursor? In this molecule over here, it's going to be, carbons, hydrogens, and oxygens. These are all non-metals, and this exists as a discrete molecule, okay? And you express the chemical formula as the number of each atom in one molecule, and we call that the molecular formula. So this is a molecule of glucose. So what would the molecular formula for a glucose molecule be? It has three elements in it, we can see. It has carbon, just deleted that, carbon, hydrogen, and oxygen, CHO. Well, how many of each does it have? The carbons are black. I count 1, 2, 3, 4, 5, 6 carbons. And we're going to put a subscript 6 over here to show that there's 6 carbons in this formula. The hydrogens, there's more of those. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 hydrogens. And how many oxygens? Those are the red atoms. 1, 2, 3, 4, 5, 6. C6H12O6, okay? Notice that the molecular formula is not an empirical formula. The empirical formula, which is that simplest integer ratio of all the elements, if I were to apply that to the glucose molecule, that would be CH2O. We don't show a 1 if that's there because it's implied. That would be the empirical version of glucose, and that's really not useful in our everyday discussion of covalent compounds. So don't really worry about that. Really just focus on the takeaway here is that for a covalent molecule, use the molecular formula, the exact number of each element in one molecule, because one molecule of glucose will be identical to another molecule or any other one in a sample. And for ionic compounds, well, you're going to use an empirical formula because ionic compounds exist as a giant crystalline matrix of repeating units. So no discrete single molecular entities. Okay, so another way to represent what a compound is using chemical notation is the structural formula. And this is a really useful tool because it gives you a hint as to what the arrangements of the atoms are within a molecule, which will give you a sense of its 3D structure. All right, it's more work to make a structural formula, but it'll give you a lot more information. Let's take a look at water, for example. H2O is the molecular formula, okay? That certainly tells you what elements compose the molecule, but if you look at a space-filled model or a line structure model, this will reveal, that water has a slant, bent geometry to it, and that the oxygen is in the middle of two smaller hydrogen atoms, and a really skilled chemist will be able to look at the structure of a compound and be able to make predictions and inferences as to what the properties of that substance would be. Okay, take a look at hydrogen peroxide for comparison. It's similar to water in the sense that they're both composed of hydrogens and oxygens, but the shape of the molecule is very different. You get this slanted structure for hydrogen peroxide compared to the bench structure of water. And that is going to have some pretty big effects on the properties of them, that, you can't drink a glass of hydrogen peroxide and expect to be, okay later that day. So there's a lot of information within the structural formulas. Another boon to knowing the structural formula for a compound is that it can alleviate some ambiguities. All right, it delineates structural isomers of a compound. So isomers, what is that? An isomer is basically two compounds that have the same formula, but they're completely different entities. So this compound over here, dimethyl ether, it is a gas. It used to be used as an anesthetic, but it's actually quite toxic. So modern medicine has grown to use more reliable anesthetics. And it has an oxygen atom sandwiched between these two, what we call methyl groups, carbons with a bunch of hydrogens on them. Also, C2H6, one oxygen, is ethanol. Ethanol you may more likely have had experience with. This is the scientific name for, alcohol, drinking alcohol specifically, all right? The difference between dimethyl ether and ethanol, of course, is that the oxygen is, kind of on the outside of this molecule, and it's going to completely change its properties and its physiological and metabolic effects upon, consumption. And, you really can't tell the difference between these two compounds just by going off the molecular formula alone. So structural formulas, they're pretty handy. Okay, now we're going to be discussing molecular and formula weights. And these words can be used interchangeably, molecular and formula weight. Basically what they are, it is the sum of the atomic weights of all atoms in a chemical formula. So if you don't have one open in front of you now, either in a separate browser tab, or I recommend, printing out a periodic table or opening it in your textbook, have a periodic table in front of you for really the rest of this lecture, because we will be referencing it sporadically throughout the lecture. So pause the video and give yourself time to have one in front of you for you to reference, or you could print it out from the internet, I don't care. Now that you have a periodic table in front of you, take a look at, I don't know, let's take a look at the carbon element square. It'll be on one of the top rows. So that is going to look, it's hard to draw straight lines on this thing, so bear with me. It will be the sixth element, so it will have a 6 at the top of its element square, denoting that it is the sixth element. And the chemical symbol is going to be C, and underneath it, it's going to have the number 12, like 12 point something. I think it's like 12.00 something. This is the atomic weight of carbon, which means that 1 mole of carbon equals 12 grams, 12 point whatever grams. It will also mean 1 carbon atom has a weight of 12 point whatever daltons, or atomic mass unit. Same thing. So a dalton is the weight of, pretty much a proton. So it's going to be a very, very small measurement of mass, but there's a relationship here, which is very intentional and convenient. All right, so this is just to review how we get this information out of the periodic table. And different elements are going to have different atomic weights. So different compounds formed of different elements are all going to have different molecular weights. And you can sort of get a visual appreciation of that in this picture over here. We have a dish full of sucrose over here. we have a vial of water, a vial of mercury, sulfur is an element. This is called potassium dichromate, this orange, beautiful cancer-causing substance, sodium chloride, copper, and lead. Now, these are all different visual amounts because their molecular or atomic formulas are all going to be different, which means that 1 mole of each of these entities will correspond to a different amount of mass. So let's apply this over here to some more elevated examples and determine the molecular weights of these two compounds. So the first we'll do is road salt. This is what they put on the roads to make them more drivable in icy weather. Calcium chloride. They don't use sodium chloride, they use calcium chloride, I believe. And this is an ionic compound. But the same rules apply. You know, what is the repeating unit here of a calcium chloride crystal? What is the molecular weight of that? Well, open up your periodic tables and consult the calcium and the chloride element squares. Now, I just happen to have memorized the calcium and chloride atomic weights because I use them frequently in my day-to-day work, but 38 atomic mass units or grams per mole is the atomic weight of calcium. And you can double check me on that because maybe my memory is wrong, but I doubt it. For chlorine, it's 35, come on, 35.45. I should do that, 35.45 for chlorine. We have 1 calcium atom and calcium chloride unit, but we have 2 for chlorine. So 38 times 1 is going to be 38. And 35.45 is going to be what? 70.9. So let's add those together. 38 plus 70.9. That is going to be 108.9. 100, I'll write it up again over here. 108.9 grams per mole of calcium chloride, or 108.9 Daltons per 1 unit of calcium chloride. The next example we can work on is table sugar, sucrose. This is a bigger molecule. It's also a covalent molecule because there's only non-metals in it. And we have carbon, hydrogen, and oxygen. Well, I told you just now that carbon has a molecular weight of 12 Daltons or grams per mole, about. Oxygen, consult your periodic table. You know, I'm going to give you the answer in a second, but I'd rather you develop the skill of figuring it out for yourself or determining it for yourself. So the atomic weight for oxygen is going to be 16. And hydrogen is pretty easy. It's going to be 1. Now let's multiply each of these by the subscript in the molecular formula, which will tell us how many of each element is in one compound. So carbon is 12. We will multiply that by 12 for the 12 carbon atoms in that sucrose molecule. Oxygen, that looks like a V. Oxygen has 16. No, excuse me. Its atomic weight is 16, but it has 11 atoms in it. All right. Hydrogen is going to be 22. So if you multiply that all together and then you add them up, you know, I want you to practice your multiplication skills right now. Do it out by hand, tally them, and see if your answer tallies up to 342. That is the answer for the molecular weight of that's the 342 grams per mole for 1 that's how many grams are in 1 mole of sucrose, 342 Daltons in 1 compound of sucrose. Okay, now another form of data that we can extract out of a molecular formula is the percent composition by element, which is to say, what percent of this element composes a given molecule or a mole of that molecule, and what is the percent composition of, the other one or all the rest. And there are many uses for this, but let's just use sodium fluoride as an example question for you to practice on. Sodium fluoride is an additive to a lot of toothpastes, and that's because the fluoride will combine with your teeth in a way to make them resistant to decay. And in this question, we are asking you, get my pen ready, we're asking you, that's a highlighter, we're asking you what percent composition of a sodium fluoride salt is sodium and what percent composition is the fluoride by weight. And at first this seems kind of maybe daunting or intimidating, but I promise you it's not hard when you break it down into these 3 steps, which is to write down the formula, determine the molecular or formula weights for that compound, and then you calculate the percentages of each individual element over the whole. And I'll walk you through that process, and you'll see that it's not as bad as you probably are making it out to be. So, okay, what is step 1? Write the formula for the compound in question, sodium fluoride. We know that it's going to have the element sodium and the elements fluoride, all right? But what's the ratio between these 2 elements, all right? So consult your periodic table and tell me how many reactive electrons they have. We know that sodium is in group 1, so it's going to have 1 reactive electron. Fluorine is in group 7, so that means it will have 1, 2, 3, 4, 5, 6, 7. Okay, we need to add up electrons until someone has a happy 8 according to the octet rule. And it just so happens that fluorine can take 1 electron from sodium to satisfy the octet rule. So the molecular formula is just sodium fluoride. That's all. Pretty easy. Now we will determine what the formula weight is, and you will also have to pull up the periodic table for that. So again, I kind of just know this, but look at the periodic table and determine what the atomic weight for sodium and fluorine are. I happen to know that sodium is 23 atomic mass units or grams per mole of sodium. Fluorine is going to be 19. All right. So since they each have 1 atom represented in the molecule, it's going to be a total of 1 times 23 and 1 times 19, which is just themselves. And the formula weight for 1 sodium fluoride unit, you really can't say molecule because it's a salt, is going to be 42 Daltons or 42 grams per mole. Okay, good. Now, what percent of that 42 grams per mole is attributed to mass by sodium versus mass by fluorine? So it's just a question of division, really. We are going to find, the parts over the whole. We know the whole is going to be, let's solve for sodium first. It's going to be 42 Daltons. 42 Daltons in 1 sodium fluoride molecule. Of those 42 Daltons, sodium composes 23 Daltons of mass. So 23 divided by 42 is going to give you like 0.54 something, 0.547, and you multiply that by 100% to get 54.7% sodium composition in sodium fluoride. We are going to do the same thing to solve for the percent composition of fluorine by listing at the bottom what the whole composition mass is, which is 42 daltons for one sodium fluoride molecule. But now we're going to divide it into the mass of just fluorine, which will be 19 daltons. You divide that, you multiply it by 100%, and that will give you 45.2%. Now, in theory, this should add up to 100%, right? But it's going to be a little bit off, a little bit shy of that. And that's really just because rounding errors, I'm using nice even numbers here. Really, the mass of sodium, I think it's like 22.99 or something like that. So, you just got to bear with the assumptions. Just make sure that you did this right. When you add up everything, it's close to 100, like within a percent off. So why are we fussing so much about all of this chemical notation? Well, the end goal, essentially, of chemistry really is the study and analysis of chemical properties, sure, but also chemical reactions, all right? And I've said this last lecture, but it really doesn't hurt to repeat that chemical reactions are a process where bonds are made and or broken. And we can communicate and describe chemical reactions through things known as chemical equations, which are a concise representation of these transformations occurring at the atomic level. And every chemical equation is going to have 3 components to it. You're going to have a reaction arrow, and what this means in chemistry symbology is a chemical reaction is occurring, and specifically one that converts reactants into products. Reactants, think of as your ingredients or your starting materials. And your products are, I think it's a little maybe self-explanatory. That is what comes out of your reaction, all right? And chemical reactions occur everywhere without you even realizing it. So the human body, any living organism, is just a bag of chemical reactions. And as long as those reactions go on, that organism will remain alive. When you cook food, for example, that is chemical reactions done on food to make it edible and more palatable, like roasting or barbecuing these steaks over here. And the act of cooking the food, well, you need a combustion reaction to generate that energy to cook the food as well. And that's something that we can dissect a little bit right now. Here's like an example combustion reaction that may occur on a gas-operated grill. You have, some methane. Okay, this is methane. It's one reactant. And you are burning it with oxygen from the atmosphere. Oxygen in the air, in general, exists as a diatomic molecule, as 2 oxygens bound to itself. And when you combine these, it will create a bunch of heat, fire, and that's what cooks the food. But, fire isn't matter. The matter that is formed is specifically carbon dioxide, CO2, and water. Really water vapor, steam, because it's so hot. All right, but there's a little bit of a problem here. Let's do some counting. All right, the number of carbons on the reactant side of this equation, there's 1, and okay, there's 1 carbon on the product side as well. But if we count the oxygens and the hydrogens, we have 2 oxygen atoms notated in the reactant side of the equation. but we have 3, 2 for carbon dioxide, 1 for water, on the product side. And you'll also notice a mismatch with hydrogens. There's 2 on the product side and 4 on the reactant side. So this is not balanced. And this is no good because remember the law of conservation of matter and energy. Matter and energy can neither be created nor destroyed. So we are creating matter according to this notation. So this is wrong. But if we balance the equation, it will give us a more accurate reflection of what's happening in a combustion reaction. And I'm going to show you how to do that in the next slide, step by step. This is the procedure that I've written out for balancing equations, which is to say to make all the equivalents of one element on the reactant side equal the number of equivalents of products on the product side. And the first step to balancing any equation is to just, in my opinion, just write out the unbalanced equation again in your own handwriting somewhere on a piece of paper. For some reason, I've noticed that students have more success when they just write it out in their own hand instead of just working off the printed version before them. So let's work with that methane combustion as an example to work with together. And we're just going to write over here CH4 for methane plus O2 dioxygen reacts to yield. Sometimes that's what that arrow means. It means yields in like chemistry talk. CO2 plus H2O. Now we know this is a lie because it's unbalanced. One equivalent of methane can't combine with one equivalent of dioxygen to yield one equivalent of CO2 and one of H2O because the elements don't match, the numbers of them on both sides of the arrow. And that's what step 2 is going to highlight. We're going to highlight the mismatches by tallying the elements of the reactants versus the products. And this is personally how I like to do it to stay organized. Draw 2 lines down beneath on either side of that reaction arrow, and between them make a column of all the elements that participate in this reaction. So we have carbons, hydrogens, and oxygens. And now we're going to tally them up on the reactant side of the equation. We have 1 carbon, 4 hydrogens, and 2 oxygens. All right. Oh, that's excuse me. That's an O for oxygen. 2. I don't know why I did that. Anyway, for the products, we have 1 carbon, so that looks balanced so far. But here's the problem. We have 2 hydrogens in that water molecule over there, and we have 3 oxygens. So we are creating oxygen and destroying hydrogen. That's not good. So how do we balance this out? Well, it turns out this reaction proceeds with more than one equivalent each of these entities, which is to say that we need to add coefficients to generate multiples of these reaction participants in order to have the number of elements on one side be equivalent to the number of elements on the other side. So this is what I mean by adjusting coefficients. You might be tempted to just be like, oh, I'm going to turn this, H2O into an H4O. You can't do that. You can only change the coefficients, which is to say the numbers before these compounds. And this is what I mean by that. We're going to draw 2 over here. We're going to double the amount of hydrogens in this term. So we're going to cross out this, and 2 times 2, 2 water molecules. Now on this side of the equation, we have 2 equivalents of water. That means we have a total of 4 equivalents of hydrogen generated. And this now matches. But you may also notice that if we're doubling the hydrogen from the waters, we have to double the oxygens within the water as well. So 2 H2O molecules, that's going to yield a total of 2 oxygen atoms plus the 2 oxygen atoms in the carbon dioxide molecule. So don't put 6 down here. That's a common mistake. What you'll want to do instead is be slow and deliberate and write down 4, because it's 2 from here and 2 from there. All right, we're almost there. Compare, see how the numbers are adding up. We're going to be adjusting the coefficients according to step 3. And we now have our oxygen mismatch still in effect. Well, that's easily fixed. All we have to do is just do 2 equivalents of dioxygen, cross that out, and bam, 1, 1, 4, 4, 4, 4. Everything is balanced. Okay, so that is how you balance a chemical equation. And I'll say it again, what these coefficients represent is that 1 equivalent of methane reacts with 2 equivalents of oxygen to yield 1 equivalent of carbon dioxide and 2 equivalents of water. Now, step 4 is, I'm not going to call it a bonus step. It's like a sometimes step, a situational step. More complicated equations that may involve more entities. Sometimes you have to do a little bit of crossing out on both sides, and you could wind up with a situation where it's like totally hypothetical, but you have 6x reacts with itself to yield 8y, okay? So this is a little bit sloppy because the coefficients aren't expressed as their lowest multiple integer. So 6 to 8 is the same ratio as 3 to 4. We just divide everything by 2, okay? So that's what I'm saying here. That doesn't apply to this example because 1 to 2 to 1 to 2 is the simplest ratio you could achieve with those numbers. But like I said, 6 to 8, that has a lowest common denominator between them, and you can divide that out and get the simplest expression, which would be 3x to 4y, okay? Now that we know what chemical reactions are and how to marry them, my goal is to introduce you to the 4 different types of chemical reactions and for you to be able to recognize them based off of the general form of their reaction equations. So the first reaction I want to highlight are combination reactions. Sometimes we call these synthesis reactions, and what makes them combination synthesis reactions is what you're doing here is you're taking 2 reactants, let's say x plus y, and you are making bonds between them to form the compounds, hypothetical compound XY, okay, bound to each other, all right? And you can kind of think of this as like the dating or the marriage reaction. It's a union between 2 separate entities. One example of this is rusting, actually. Rusting is kind of a form of combustion. We have 4 equivalents of iron reacting with 3 equivalents of dioxygen to yield 2 equivalents of iron oxide, okay? And it's anytime you have oxygen binding to something, that is, you can think of as a form of combustion, but instead of making a lot of heat and fire, this reaction occurs very slowly and it turns, iron into this brittle, flaky, nasty orange compound, all right? And this is rust over here, all right? Next up, we have the opposite of the synthesis/combination reaction. This is known as a decomposition reaction, all right? Think of this as the divorce or the breakup reaction. Instead of having x plus y yields xy, you have a compound of xy chemically bound to itself, bound together, and you're breaking the bonds between them to form x plus y, okay? It's the breaking down of a complex compound into simpler compounds, or their bare elements. A pretty example of this is the decomposition of mercuric oxide shown over here. It's a really cool orange solid. It's also quite poisonous. Painters used it in orange paints back in the day before they realized how bad it was for you. And what this little delta means, that can mean, time, or you heat it up a little bit. And when you do that, you will break apart, you'll decompose this into its constituents, elemental mercury and dioxygen gas. And this up arrow, that means that that product is escaping, all right? And you can see that over here. We have this little bit of red at the bottom of this test tube, and it must have just been heated, and you see this elemental mercury, this silvery stuff, being deposited on the glass on the inside. And you really can't see dioxygen because it's a colorless gas, but you can trust that it is now outgassing because it decomposed. Okay, these reactions are pretty cool. The next class is single replacement reactions, and the metaphor that I like to use to describe them are that these are homewrecker reactions. And an example of that is this copper chloride with aluminum reaction. And to break this down a little bit, what we're seeing here is an atom or ion that's within a compound is being replaced by a single atom or ion that's not in a compound. The general reaction scheme for this is xy plus z, where z is the homewrecker. And what that's doing is z is more reactive than y. So it is getting in there, interfering with the relationship, and kicking out y as the third wheel. And xz becomes the new compound form with y being liberated. And an example of that, a more concrete example of that, is this reaction of copper chloride and solid aluminum metal. So you see over here the aluminum metal, which is this. This is solid element, and we're going to put it in a solution of copper chloride, which is blue. Okay, copper and water. Copper ions in water look blue. Now, the aluminum wants to be with the chloride more than the copper. So what happens is we're going to displace or replace the copper from this equation, and we're going to be left with elemental copper. And we're going to form a colorless aluminum chloride salt. And elemental copper is like brownish, reddish brown. Copper ion in water is blue. And you can see here that we have the aluminum bar dunked into the blue liquid. This has copper. The copper mostly, well, it's black on black, but it mostly moved over here. Okay, that's elemental copper. That was taken out of the solution and deposited onto the site of the swap, which was the aluminum bar at the interface of the solution to the aluminum. So that's kind of cool to look at. It's very dramatic. Okay, this is the last class of reaction. And this also is kind of a cool one, in my opinion, the double replacement reaction. And this occurs when you have two compounds that interact with each other and they swap their partners. So if you had AX compound reacting with BY compounds, you would form AY plus BX. And the trick here to make this sort of work is that you need to form one of three different things as the product. It needs to form a solid precipitate that will crash out of the solution and prevents basically these partners from swapping back to their original partners. It needs to form an escaping gas, which will waft away and then that would also prevent things from swapping back to the original configuration, or it would react to form water, and we'll see an example of that at the end of the lecture, where water is a very stable compound and it's not going to react anymore, and that will also drive the reaction towards the products or to completion. Okay, and here's a really beautiful example of that. In this GIF, we have a solution of potassium iodide being added to a solution of lead nitrate. Both of these are clear colorless salts, and they form clear colorless solutions when dissolved in water. I should also mention that nitrates, NO3, this is an example of a polyatomic ion. All right. So polyatomic. Which is basically, it's a compound with charge. So nitrate has a -1 charge. Lead, in this case, has a +2 charge. So this acts like a salt, even though there's a covalent compound in it. It's a covalent compound. So 2 -1s balances out the +2 of the lead. That makes it, a stable salt, even though it has a covalent component to it, which is kind of cool. Anyway, sorry for that aside. 2 potassium iodides react with 1 lead dinitrate, because there's 2 nitrates in that salt. It reacts and you swap the partners. The iodides go to the leads and the nitrates go to the potassium. 2 potassium nitrates form. These are super soluble, no color. Lead iodide is this beautiful yellow color, and it looks like a yellow liquid that's actually like a yellow fine dust that will settle into a powder over time. But that forms immediately upon contact with the solution, because this lead iodide compound is really poorly soluble, it turns out. So it's going to form a precipitate and crash out of solution, and it's not going to want to go back to the original lead nitrate and potassium iodide configuration. Lead and iodide love each other that much, they can't be separated, ever again in this scenario. And so this, again, is a very dramatic, kind of cool representation of a double replacement reaction. Okay, now chemical equations are useful because they are essentially the recipes for making a compound. This over here is the recipe, for example, for making ammonia, all right? We have 3 dihydrogen molecules reacting with 1 dinitrogen molecule to yield 2 molecules of ammonia, NH3. So one interpretation of this is that we have a representation of the molecular ratios of reactants to products. Said in plain English, this is how to make 2 molecules of ammonia. But let's face it, 1 molecule, 2 molecules of ammonia, even 1,000,000 molecules is too little to be useful. We want to make gajillions of molecules of ammonia to use, like a mole or 2. A mole is 6.02 times 10 to the 23. That's a huge number. That's a lot of molecules of ammonia. But in real life, that's not going to fill, a bottle of Windex. But just to use this as an example, though, if we scale this up to the mole ratio, instead of saying 3 molecules of dihydrogen plus 1 molecule of dinitrogen, we could say 3 moles of H2 plus 1 mole of N2 yields 2 moles of ammonia gas, which is saying 3 times 6.022 times 10 to the 23 molecules. But since that's annoying to say, we just use moles as a shorthand. So that's a second possible interpretation of a chemical equation. It's the mole ratios of reactants to products. Well, that's, perhaps at a more useful scale. However, we really can't measure moles out directly. There is no mole machine or counter where we put something in and it says, we've got a mole of this stuff. No, we need to use the periodic table to infer how many moles are in a sample based off of the formula mass or the formula weight or the molecular weight. All right, moles are really useful for showing how equations pan out, but we have to measure the ingredients in, let's say, grams, because that's what our instruments are capable of doing easily. So said another way, look at your periodic table and tell me what the mass ratio of this chemical equation is. 3 moles of dihydrogen gas, we all know by now that 1 mole, the atomic weight of hydrogen is 1 atomic mass unit or Dalton or gram per mole. We have 3 dihydrogen molecules. That's 3 times 2 times 1 equals 6 grams, corresponding to 3 moles of dihydrogen gas. Nitrogen is 14 Daltons or atomic mass units. 1 mole of dinitrogen, multiply that by 2 to get 28 atomic mass units. Also grams per mole, same thing. So now we know if we measure out 6 grams of dihydrogen gas, we know we need to measure out another 28 grams of dinitrogen gas to react with the dihydrogen to yield 34 grams of ammonia. And we know 34 grams of ammonia will be produced every single time, assuming the reaction goes to completion, is because 1 equivalent of nitrogen is 14, 1 equivalent of hydrogen is 1, and we have 3 of it. So 3 plus 14 is 17, and oh wait, we have 2 moles. Multiply this by 2, and we get 34 grams per, not 34 grams per mole, but we get 34 grams in total. All right? So there's a lot of information that we can extract out of the chemical equation. Okay? That's why I spent so much time, discussing this and leading up to this point. This is one of the most important slides of the lecture. However, the hard part about chemistry is not just writing out this reaction and calculating how much product you'll get and ta-da, then you make money when you sell that much ammonia to the Windex company. No. The hard part is really discovering the conditions and the temperature and the mixing times of the reactant substances to get the full, 34 grams out of the efforts that you put into setting up this reaction. And 99 times out of 100, the way that chemists get things to mix and react well is by dissolving them into the same liquid and using that as the way of mixing them and getting them to react. And that's going to compose the second half of the lecture, which is going to concern solution states of these entities. Since solutions are going to be the topic of the rest of this lecture, it behooves us just to go over the basics and some definitions about solutions, because you probably think about solutions in your day-to-day, but there's some terminology that's chemistry specific that I do want to cover. In chemistry land, a solution is simply a solute plus solvent, or solute dissolved in solvent. The solute is something that will be dissolved. It could be, powder, solid, or it could be, another liquid, frankly. And a solvent is the word for the liquid dissolving the solute. And in the case where you have 2 dissolvable liquids, liquids that dissolve in each other, called miscible, that would be, the solvent would be whatever liquid is in a greater proportion, really. Some common examples, everyday examples of solutions that you might be familiar with is, lemonade. Lemonade mix would be the solute. That would be, a mixture of sugar and flavoring and yellow food dye. And you dissolve that in the solvent, water, all right? The mix plus the water. So yeah, water is a very, very common solvent that we use, in the day-to-day. And it's not the only solvent, though. Alcohol, for example, is another common solvent. That's the solvent used in fragrances and flavors, like the extracts at the supermarket. Fragrances, perfumes, right? And that would be, it's a solution of alcohol that contains essential oils as the solutes. And you can have, cheap perfumes, right? Or cheap colognes. These would be dilute solutions because they don't have a lot of the essential oil in it. A weak lemonade would, by the same extension, be a dilute lemonade. It wouldn't have a lot of the mix dissolved into it. And a concentrated solution that has, a lot dissolved into it. And, this can be subjective, of course, like I, for example, like sour things. So for me, a perfect lemonade might be considered concentrated by normal people's standards. And a saturated solution is one where you can't dissolve any more of your solute into it, all right? So no matter how much you add, it'll get to a point where that excess solute is going to settle at the bottom of the jar, all right? And this doesn't happen really with miscible liquids, but it does happen with solid solutes, okay? So, like, for example, my, little sister, when she was younger, she really liked, chocolate milk, and she would put more and more chocolate syrup into the glass and stir, 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 and there'd be this black sludge collecting at the bottom, and I would say, oh, it's saturated, you can't put any more in there, it's just wasting the syrup, but she, ate the leftover syrup with a spoon anyway. So there you have it. Now, I also want to mention these are examples of, polar solvents that have dissolved solutes in it, right? You could have nonpolar situations as well, nonpolar solutions. So gasoline is a mixture of a whole bunch of different liquid state hydrophobic compounds that are used that you can burn for fuel. So solutions come, all different flavors and all different concentrations and all different chemical makeups. Now, I mentioned on the previous slide that water is an example of a solvent. It's a very common solvent, all right? The reason why it's one of the most common solvents is because it's one of the most polar compounds, in our repertoire, all right? And if it's really polar, that means it's going to have really strong cohesive and adhesive forces. So let's write that down. So polar usually correlates with good molecular cohesion, all right? And so why is that? So this is because, and I know I've mentioned this before, but I can't repeat it enough, it's so important. Water has a few things going for it on the structural side. It has this bent shape that exposes or groups these negative electrons from the oxygen atom on this side of the molecule. And it's not going to make it negatively charged, but it's going to give a partial negative charge to like this half of the molecule. And conversely, the hydrogens, they only have 2 electrons. There are exceptions to the octet rule. And those 2 electrons are going to be occupied in these 2 bonds to the oxygen atom. So that's going to leave these hydrogens, the positive nuclei of these hydrogens, exposed, making a positive half of the molecule, partial positive half, to complement the partial negative half. All right. Now, when a hydrogen is bound to an oxygen, that is going to really make the hydrogens kind of their nuclei exposed, and it's going to really draw these electrons towards this part of the molecule, and it's going to really exaggerate these partial negative and partial positive charges to the point where it's going to make a very strong form of polar interaction called a hydrogen bond. Okay, and this is the basis as to really all of water's properties and why it's such a good solvent, because it can form hydrogen bonds. So a few things to know about hydrogen bonds: they are not bonds. All right, that's a lie. They're not bonds. They are strong polar interactions, though. And they occur between multiple molecules. So the slightly positive portion of this water molecule is going to feel an attraction to the slightly negative portion of that molecule. And that's the basis of the cohesion that we see in water. This will also be the basis of its adhesion to compounds, polar compounds, that are not water. Let's examine how these cohesive forces enable water to be a good solvent. So we'll first examine how water dissolves ionic compounds, all right? Now, how dissolution of a salt works. Recall that a salt is not a molecular solid, it's a crystalline solid, where the metal and then the non-metal form these lattices, these crystal lattices, all composed of these, ionic bonds, holding them together electrostatically. So this is like a salt cube or a salt crystal. All right. Now imagine we put that salt crystal in water. I just told you that water has zones of partial positive and partial negative areas. And salts are composed of literally positive and literally negative ions. So the water is going to be attracted to the components of the salt crystal, and it's going to basically outnumber and overpower the ionic bonds, all right? So it's going to outnumber and overpower, and it's going to break it apart. And it's going to break it apart like so. The chloride, which is going to be negative, is going to be attracted to the partial positive charges on the hydrogen side of the water molecules, and it's going to form these hydration shells or these solvation shells, and it's going to carry those ions apart and away from each other. And the reverse is going to happen to sodium. So the sodium ion we know is positive. That's going to associate with the negative portion of the water molecule. And that's what this solvation shell is going to look like, or hydration shell. This is the mechanism by which compounds dissolve, specifically salts, which are ionic compounds. Now, molecular compounds, it's similar. So what's happening here is that in this picture, we have a glucose molecule, or a sucrose molecule actually, which is a sugar. And the sugar has these red and white groups to them, which are oxygen and hydrogen groups, like that, OH. And water has oxygen, hydrogen groups as well. It's like H2O, right? And we're going to form polar interactions, hydrogen bonds, between these groups specifically, all right? And let's say you have like a sugar crystal, it's going to be a bunch of these sugar molecules that are going to be, glommed together, not by bonds, but by cohesive forces between sugar and sugar, but still the polar interactions between the solvent and the solute is going to outnumber and overpower the cohesive forces of the solutes that hold it together. We're not breaking apart ionic bonds, we're just breaking apart whatever attraction is holding that blob of sugar together, okay? And it's going to disperse in the solution. And here's a picture of that. We have water, all right? And we've broken apart the sugar molecules that were clumped together. They're still individual molecules. We're not breaking covalent bonds, but we're just spreading them apart in the water, okay? So very similar how molecular solids and ionic solids dissolve. Okay, it's a common misconception that I'll see in some textbooks that water is a universal solvent, all right? Yeah, there's no such thing. Universal solvents, they don't exist. And that's a good thing, because if you had a solvent that could dissolve anything, if you put it in a jar, it would dissolve the jar that it's residing in, and it would fall to the floor, hopefully not your feet, because then it would dissolve straight through the floor, straight through the dirt, straight through the earth, and dissolve all the way down to the core of the planet, all right? That would be quite a dangerous liquid, all right? So universal solvents do not exist because solvents have preferences. I've said time and again that water is a polar solvent. Polar solvents are going to form these cohesive attractions with other charged or polar entities like sugar or sodium chloride salts, all right? There's this mantra of like dissolves like that will be very important to know for chemistry. On the flip side, nonpolar solvents are going to exclusively dissolve nonpolar solutes. And we typically encounter these less in day-to-day because they're usually not as safe as water, okay? An example of that would be, think of water and oil, like in this GIF over here. We're pouring oil into water. They are non-miscible liquids because oil is very nonpolar and water is very polar. So they don't like each other. They're not going to mix well, okay? And this may make you ask, well, what makes a compound nonpolar? Well, there's two things to consider, and it kind of goes down to structural formulas and a little know-how about basic chemistry. Some good rule of thumbs is to look at the structure or the formula of the compounds and ask yourself, is it mostly carbons? Okay? Carbon tends to make things very nonpolar. This is a structural formula for a fat molecule, okay? This is a fat molecule, also called a lipid. And it has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 times 3, so 32, 48, and 51, 1, 2, 3, carbons in it. All right, this molecule is mostly carbon, so it's mostly going to be quite nonpolar. All right, that's a clue that it's not going to dissolve in water very well. Another clue that would tell you if a compound is nonpolar is look at the shape. Is it symmetrical? Symmetrical usually means, symmetry usually means nonpolar. So CO2, carbon dioxide, it's only got one carbon atom. It's only 33% carbon. It's got two very polar carbon oxo bonds, double bond O, but it's a symmetrical shape. Okay? So you got negative, negative, positive, positive, and they kind of just like cancel out these partial charges, and it makes it a very nonpolar molecule. And for the oxygen, dioxygen molecule over here, this is also nonpolar because you kind of got like an even tug of war over here. Both oxygens are pulling on these electrons in the bond with the same strength, so it cancels out, and it's not like you're going to have these groupings of electrons throughout the molecule. All right, so symmetry equals nonpolar, bunch of carbons equals nonpolar. All right, and that's why they're not going to mix with polar entities. They would rather mix with other nonpolar entities. Now, what if I told you, though, that molecules can be both polar and nonpolar? These are pretty cool, I think. The word for them is called amphiphile. And amphi in Greek means both, and phile means like. So amphiphiles are compounds that like both polar and nonpolar solvents because they have both polar and nonpolar regions. An example of this is soap, okay? Look at this soap molecule. We have a long chain full of carbons in it that looks quite symmetrical. This is going to be the water-fearing ends of the compound. This part of it will be hydrophobic, like phobe meaning fear. Hydrophobic or nonpolar. Those aren't always synonyms, but for this course they can be. On this side of the molecule, it's actually charged, you know? It's got this sodium ion complexed with a negatively charged oxygen molecule on atom, on this end of the molecule. So this part is going to be soluble in water. This will be hydrophilic. All right, and this is really cool because this is the molecular mechanism by which soap works. This is a cartoon of, maybe you were playing soccer and you got mud on your clothes. Mud and dirt is very oily. It's very hydrophobic, all right? Very nonpolar. You apply, you could rinse it with water all you want. Those dirt stains aren't going to come out. But if you add soap to your wash, the hydrophobic tails of the soap molecule will dissolve into the hydrophobic dirt clumps, and in turn, the charged heads that are water soluble will be sticking up exposed to the wash solution. So when you rinse it out, it will be able to carry out the dirt from your clothes and wash it away, like so. So knowing how soap, if you could understand how soap works, you've got a really good grasp on solvent affinity, polarity, and all these really crucial concepts to solutions chemistry. Because we are scientists and we like to be quantitative and measure things accurately, when it comes to concentration, it's really important that we be able to express how concentrated a solution is numerically. Because I sort of alluded to this a few slides ago when we introduced the terminology of solutions. Concentrated and dilute are subjective, and scientists typically don't like to use those in formal contexts. Using that lemonade as an example, I said that I love sour foods. There's no such thing as a concentrated lemonade in my book, but a normal person would probably think my lemonade is concentrated. So if I were trying to write a recipe book and I wanted to be specific and reproducible with the concentration of lemonade that my recipe calls for, I need to find a way that would express the recipe with numerical accuracy so it would be the same concentration for everyone who ever made it. Okay, and there's a few approaches to measure concentration actually. The first example is volume by volume. So this is used for solutions that have liquid solutes, and an example of that would be nail polish remover. And you express that as the percent of the volume of liquid solutes in the total volume solution. And isopropyl alcohol, 70% isopropyl alcohol nail polish remover is like this. If you were to have, let's say, 100 milliliters of this stuff, 70% would be isopropyl alcohol, and that last 30% would be water, okay? I think it's a common mistake that people think, oh, it's 70 mils of isopropyl alcohol and 100 mils of water. That's not the case. Another way to measure concentration is by weight. This is used for solids that are, for solid solutes, excuse me, and when you dissolve these into a mass of solution. So quick recap for water, let's say 1 mil at room temp, it's going to be 1 gram because that's what its density is, 1 gram per mil. Medical saline is 0.9% sodium chloride in water. If you don't know, medical saline, shown over here in this bag, is a solution that you can get at the hospital if you have like a drip or if you're dehydrated and you need to be rehydrated intravenously, and they're going to put a certain amount of salt in here that will match the ideal salt concentration in the human body. Okay, so because you don't want to do too little, too much salt, that'll be dangerous. And how this medical saline solution is made is they take, for example, 9 grams of sodium chloride and they dissolve it in 1,000 grams of solution. Okay, notice how I said solution and not water. It would not be appropriate to dissolve 9 grams in 1,000 milliliters of water because that wouldn't be 1,000 grams of solution. 9 of these grams is going to be attributed to the sodium chloride. All right, so just think about that for a second. Be very careful because I think I see a lot of mistakes, particularly with this expression of concentration. All right, it is in grams of solution. Think of another way. If you were to get this is how you would make it in the lab. You had a graduated cylinder that was 1,000 mils. What I would do is I would put the salts, that 9 grams, directly in here, all right? So we're already accounting for that mass and volume, and then add in the water and bring it up to the 1,000 mil mark, okay? That's how you would make it. The way that chemists typically prefer to measure concentration is with a unit you perhaps have not heard before, and that is molarity, all right? Molarity is just a fraction of the moles of solute that you have dissolved in the liters of solution. This, in my opinion, and probably in most chemists' opinion, is the most useful measurement for concentration because it's telling you how many molecules exist in a solution, all right? How many molecules of 10 grams of salt is going to be different from 10 grams of sugar, okay? But if we know that we have a 1 molar solution, that's like the term we use for concentration, it's molar. 1 molar salt will have the same number of particles as it dissolved as 1 molar of sugar, let's say, or anything for that matter, because it would be 6.022 times 10 to the 23 things in 1 liter of solution. If we were to say that, there was 1 mole existing in that liter, mole per liter, okay? And, it's not a difficult fraction, but sometimes you have to do some conversions and there can be a little bit of work involved when calculating molarity or concentration as moles per liter. So let's use medical saline to practice. I'm going to tell you that we have, let's say, 1 liter of this stuff, this medical saline, and I told you it is 0.9% weight by volume of a sodium chloride solution, I would like for us to calculate the molarity of that solution. So what I'm asking you is how many moles exist in that 1 liter. So what I like to do before starting out any kind of problem is I like to write down all the data that I know and then see what formulas that correlates to and work from there. And also write down the things that I don't know. That could also give me a hint on how to solve the problem. So we don't know the molarity, capital M. That's what we're solving for. Well, to solve for molarity, we need the moles of sodium chloride divided by the liters of solution. This is what we're aiming for. We know we have 1 liter of water, well, of solution, because I told you it was 1 liter of saline. Of solution. The moles, we don't know yet. I'm trying to make that less sloppy, but I made it worse. There, that looks like moles now. We don't know the moles. But hey, we do have a sense of what the concentration is. We know it's 0.9% sodium chloride. So how many grams is 0.9%? All right, that is going to be 9 grams. Oops, let's write it over here actually. 9 grams divided by 1,000 grams of solution, which we know is 1,000 mils, which we know is 1 liter, okay? And 9 divided by 1,000 is 0.9, so that tracks. So the question now becomes, 9 grams of sodium chloride equals how many moles of sodium chloride? We can figure this out. You need to whip out that trusty periodic table and ask ourselves, what is the formula weights, molecular weights, whatever you want to call it, of sodium chloride? So I can tell you that sodium, and pause the video and find this out for yourself before you just let me give you the answer, because this is an important skill. It has 23 grams per mole. Chloride is 35.45 grams per mole. And there's only 1 of those elements each in sodium chloride, so we only multiply them by 1, and then we add them up. And that's going to give us 58.5 grams per mole sodium chloride. So in 1 mole, we are going to have 58.5 grams. The question is, we don't have 58.5 grams, we have 9 grams. Well, how many moles is that? Okay, well, it's going to be less than 1 mole because it's less than 58.5, but this is how we're going to do the conversion. We're going to start with what we got, and we're going to end with what we need. That's 9 grams, even though it looks very sloppy. We're going to multiply this by the conversion factor. And the unit we want to get rid of needs to be on the bottom. So 58.5 grams per 1 mole sodium chloride. The grams cancel out. You multiply 9, and then you divide it by 58.5. And this is going to be, I believe, 0.15. 9 divided by 58. Okay, yeah, about 0.15 moles. We're almost done. This is what we were looking for. Equals 0.15 moles. Okay, now we can solve this equation. Okay, moles of sodium chloride divided by liters of solution. It is 0.15 moles divided by 1 liter. And that happens to be the same number, but different units, 0.15 molar, capital M. Put a line over here. This is the answer, because moles per liter equals capital M for molarity, molar. All right, it's a simple equation, but sometimes there's a lot of work sort of buried behind the scenes. So this might be a good slide for maybe you to pause and rewatch, because there were a good number of steps here, but I hope that you do find them all to be logical after maybe repeating this exercise a few times. But yeah, this is a good skill to know. Now, something that you may already have an intuitive sense of is that solubility is a property that's unique to every solvent and every solute, and it is subject to change. So when you have let's say water, and you are trying to make syrup, for example, if you just pour sugar into water, it's not going to really dissolve very nicely or very quickly. But if you heat it up, all that sugar goes into solution and it disappears. So that's an example of solubility changes. So the solubility of a compound, usually a solid solute, is going to increase as a function of temperature. So take a look at this graph over here. These are 4 different salt compounds: sodium nitrate, potassium chloride, and sodium chloride, which is table salt. Okay, so these blue lines represents the solubility of these different entities at a given temperature. And the solubility is expressed not as molarity. I figured you needed a break from molarity, but it's the grams of that solute dissolved in 100 grams of water. So they all start on the lower ends at very cold temperatures, so almost freezing. You know, potassium nitrate is a dramatic example. You can only dissolve 10 grams of it in 100 grams of water. You increase that to, room temperature, and it's going to be around 35 grams of potassium nitrate dissolved in 100 grams of water. That's more than triple. That's a huge increase. And you go even higher and the solubility just goes through the roof. So this really is a nice dramatic example of how when you increase the temperature, you're able to dissolve more of something. Sodium chloride is a surprisingly boring example of that. It barely goes up by 1 gram, going from almost freezing to almost boiling. But these properties, as you can imagine, are unique to the different solutes. Now, as a slight caveat, the trend reverses for gases. So gases, pretty much in general, all have very poor solubility in water, but it's non-zero solubility. I don't know how to do I can't do the conversion in my head very easily, but I know that, for example, that saline solution was 0.15 molar. Dissolved oxygen in water is 0.25 micromolar. So it's 1,000,000 times less. That micro means 1,000,000th of physiological saline. So it's quite small compared to solids. But get this, as you heat it up, the solubility of gases is actually going to decrease even more. And this is actually a problem in the context of global warming, because fish gills operate by very efficiently extracting out dilute oxygen gas dissolved in water and incorporating it into their body. As we warm our planet, the oceans get more warm, and that dissolved oxygen is actually going to outgas, and it's going to be less available for the fish. And in areas where there's like, near, for example, factories, they will pump in river water to cool down, bits of machinery and release that warmed water back into the river. Well, those factories are increasing the temperature of the water, and that's going to decrease the solubility of oxygen, and you get these massive fish die-offs, which really interrupts the ecosystem. So this is an example of how knowledge of solubility trends actually has an environmental impact. Another solution property that solutes can have on their solution is a change in their boiling point and their freezing point. And the term for this that might be good to keep in your head is boiling point elevation, freezing point depression. So remember those phrases. And this is what they mean and why they happen. Let's first talk about boiling point. When you dissolve a solute into a solution, that solute is going to grab on to those solvent molecules that are attracted to it, that solvation shell or that hydration shell. And it's going to kind of act like a glue, and it's going to hold on to the solvent and make it harder for it to leave the liquid phase. So as you increase the temperature, you not only have to break the cohesion between solvent molecules, but also the cohesion to the solute molecules as well. And that's why you may have to use a higher temperature to get a solution with solute in it to the boiling point, all right? Another way to look at it is that the solute particles will be displacing the solvent particles on the surface, and that's really where that phase transition happens from liquid to gas. And so this is going to be another factor that's going to hinder boiling or vaporization of that liquid, because these solvent molecules have to not only break these additional attractive forces to the solute, but navigate their way to the top and become free. So boiling point is going to increase the saltier a solution may get, okay? As a consequence of these attractions to the solvent molecules. Now the opposite happens with the freezing point. Salt water is going to boil at a higher temperature and it's going to freeze at a lower temperature. And the reason why that happens is that the solutes interfere in the crystal network of the solvent's solid phase. You may know that water, ice, forms these very intricate hexagonal networks in the solid phase. They are very beautiful. This is why you get snowflakes, for example. If you were to have, an ion here, an ion there, ion everywhere, all at random, okay, they're going to be introducing competing forces. They want to be solvated at at any temperature, but at colder temperatures, water is going to want to stick to itself in a very specific way. And these are physically in the way of making these nice hexagons, and they're also, they're persuading these water molecules to not be in hexagons, but to rather be crowded around these positive and negatively charged ions, okay? So you're going to have to take more energy away from the system, make it colder to convince the water to settle down and leave its ion partners. So this is what we mean by decreasing the melting point. Okay, in addition to all of that, another property of solutions that can change depending on what solute is in it and how much is the conductivity of it. We can group solutes into two different categories, electrolytes and non-electrolytes. electrolytes are going to be ionic solutes, which would be salts, another word for that, typically. Okay? Salts are formed of charged ions, okay? And when you put them in solution, the solution acquires a charge as well. And if you were to hook up 2 electrodes into a solution that had, let's say, sodium chloride in it, all right, the power source would be able to reach and turn on this light bulb because the ions will help the charge jump across these 2 electrodes and complete the circuit. Non-electrolytes are going to be solutes like sugar and alcohol, molecular compounds, non-ionic, non-salts, because they have no charge, okay? And if you put these 2 electrodes in water and there's nothing to help connect them indirectly, then this circuit is going to remain open and that light bulb is not going to turn on, okay? So believe it or not, you know, water is a rather poor conductor. It's not when they say, you know, don't go to the beach or don't go to the pool when there's a thunderstorm, the concern is not that the water is going to conduct that electricity towards you. The concern is that pool water is very salty, ocean water is very salty, and that is why that is a hazard. Because water itself is actually a non-electrolyte as well. Except now I'm going to contradict myself slightly, but I will explain. I know I just told you that water is not ionic, it's not an electrolyte, yada yada. Well, I kind of lied. Pure water will weakly ionize itself through a specific process called autoionization. And this is the chemical reaction for this. You have 2 liquid water molecules in solution, and very rarely they will combine in a way and have one water molecule steal the hydrogen nucleus or the proton from another one, and it will form 2 entities, hydronium and hydroxide. That's what they're called. H3O plus is called hydronium, and OH minus is called hydroxide. And this, in a glass of any solution or water, does not happen very, very often or largely. The concentration of both of these in just standing water is 1 × 10 to the minus 7 moles per liter. That's 0.00000001, right? 1, 2, 3, 4, 5, 6, 7. This is why we use scientific notation, because it's hard to count those zeros. All right? Per 1 liter, which is 0.000000 molar. Okay? It's also, this is milli, 0.1 micromolar. Really dilute amounts, okay? Remember that 0.9% medical saline was 0.15 molar, okay? So really dilute. There's not a lot of this stuff. So it's not supercharged. That's why water is still a non-electrolyte. I wasn't lying, I promise. But these are really important components to solutions because this is going to introduce the concept of pH, and you may have heard of this before. pH is the power of hydrogen. Really, they mean power of hydronium. Okay, but same thing. It's the power of this. And what we mean by power, it's the power or exponent term of its concentration. So it's times 10 to the negative 7. Just ignore the negative part. And at neutral, by definition, a neutral solution that is neither acidic nor basic will have its hydronium concentration be equal to its hydroxide concentration. But solutions where we increase the hydronium content, these will be acidic solutions. Solutions that are the opposite of an acid, a base, these are going to have more hydroxide and less hydronium by consequence, okay? So they will no longer be equal to each other. They will be out of balance. And that has really profound effects on the property of the solution. Okay, acids and bases. So you may recall from the previous slide that I told you that an acid increases the hydronium content in a solution, whereas a base increases the hydroxide content. So how do we go about achieving that? Well, we dissolve acidic or basic solutes into water that will react with water and change those ratios directly. So let's first talk about acids, because I feel like people are more familiar with those. Believe it or not, a lot of acids are often non-metal hydrides. So you take a non-metal like chlorine and you react it with hydrogen and you get HCl, hydrogen chloride, also known as hydrochloric acid. So this acid compound has a really weak bond between the hydrogen and the chloride. It wants to just fall apart, and water greases that wheel. When you dissolve hydrogen chloride into water, that water is going to attack and take that proton, all right? And it's going to form H3O, hydronium plus, with chloride negative as the leftover product, okay? And you can see that represented here as the molecular formula. H2O plus HCl yields H3O plus chloride negative, okay? So what we're doing here, to reiterate, we're donating a hydrogen ion, sometimes called a proton, to the water. Bases are the opposite procedure of that. So a common base is sodium hydroxide. This is lye, also known as oven cleaner. That's a horrible E. Lye. Common bases are metal hydroxides. So sodium hydroxide, potassium hydroxide, these are all really powerful bases. And what happens is kind of like the opposite to what we described in the acid process. We have sodium hydroxide, and instead of this, instead of it giving a proton to water, we're going to take a proton away from water, okay? And when that proton leaves, we're going to be left behind with a hydroxide ion, OH-. And that hydroxide that was bound to the sodium hydroxide will become water in turn, because now it's going to have 2 hydrogens to 1 oxygen. And that sodium is not going to, be ionically bound to that water anymore, so it's just going to fall apart and you're going to get, sodium ion dissolved in solution. So you can appreciate how, acids and bases kind of behave oppositely to each other. Okay, that's nice, you may say. Well, what's really, though, the significance of a solution having a lot more hydroxide in it versus a lot more hydronium? Well, let's do a quick overview of acids, for example. Acids, some properties to know about them is that they have a sour taste when they're dilute. They are corrosive and dangerous, though, when they're concentrated. Now, I don't recommend you go about just tasting a bunch of acids in lab. That's a great way to lose your tongue forever. So we developed this material called litmus paper That's a safe way of determining if something is an acid or base without drinking it. And it has this property where if you dip it into an acid like white vinegar, it will turn that strip red, okay? Some other properties of acids is that they react with certain active metals like magnesium and zinc to release hydrogen gas. That is how metals dissolve and corrode in these acidic solutions. So think about, I don't know, since it's like Halloween season, I believe it was the horror series Saw. Perhaps you've heard about those, where people have to go through these horrific, challenges and hurt themselves in order to survive. In the third movie, there was a victim that was in this, trap, and she had to get a key to unlock herself, to free herself from it. But the key, metal key, was dropped into a jar of acid before her, and she had to reach into that corrosive acid and grab it as it was attacking her flesh before it would dissolve the key away entirely. But it didn't work out, and she still died very sadly. But that's a grotesque but good visual as to what the properties of acids are. Bases, to some extent, they are the opposite of acids. They don't taste sour when they're dilute solutions. They taste bitter. But like acids, they are still corrosive and dangerous when concentrated. You don't want to dip your hand in an extremely acidic or an extremely basic solution. They'll both give you a chemical burn, just through different mechanisms. And because strong bases are also very dangerous substances, we developed litmus paper to be able to detect bases in a distinct way. Instead of turning red when exposed to a base, a litmus paper will turn blue. And in this picture, it's turning blue in the presence of a solution of baking soda, which is a mild base that you would probably have in your kitchen cabinet. And another property about bases that's worth knowing is that they react with oils to form soap. If you were ever, doing laundry, for example, and you were using bleach, which is a decently strong base, and you got it on your fingers, you may have noticed that your hand would feel very slippery before it would start itching and burning. And that's because the base of bleach is actually reacting with the oils on your fingers to turn it into a kind of soap, actually. So that's also something worth knowing. Now, another way to think about acids and bases is that acids, when you dissolve them in water, donate a proton or a hydronium. But for this slide, we're just going to make it easy and just describe it as a proton, H+. Proton donor. It generates protons into solution. I used black. That was a mistake. The red means nothing. For bases, you're going to donate hydroxides when dissolved in water. Okay? So not only do acids react with water and bases react with water when you dissolve it in them, they also react with each other, and this is kind of cool. So let's predict, like a scientist would, the reaction products of HCl with NaOH, okay? So this is going to require a little bit of drawing, so just take your time and bear with me. HCl aqueous, and that parentheses AQ, aqueous, means that this entity is dissolved in water in this reaction, plus NaOH, sodium hydroxide, Li, AQ, also aqueous, dissolved in solution. It's going to react and it's going to form, something. We don't know quite yet. All right? So how do we figure that out? Well, I just told you that acids donate protons when they dissolve into water, and bases donate hydroxides when they're dissolved into water. So these are going to dissociate We can think of it that way. We can split these apart. Remember, hydroxide is like a polyatomic, so we're not going to break the O and the H, we're just going to break the OH from the sodium, all right? But let's just write it out here. H plus proton ion, aqueous, plus chloride ion, also aqueous. That looks like 2 Q's, but that's an A. Plus sodium ion, aqueous, plus OH ion, aqueous. And what could this react to form? So what are the ways that we can combine these 4 entities? We could recombine sodium with the hydroxide and the proton with the chloride, but acids don't have a strong affinity for their protons. They like to donate those, so that's not going to happen. And hydroxides, don't have a strong bond to their metal ions, so that's really not going to happen either. Would the chloride react with the hydroxide? No, that wouldn't happen, because the chloride, that's going to be negatively charged, and that's not going to want to hang out with the negatively charged hydroxide. Same goes for the sodium and the proton. That's not going to react with each other. All right, well, what's the only other option? We could, however, have the sodium react with the chloride and form sodium chloride, aqueous. Plus, this is kind of interesting, hydrogen hydroxide, HOH. There's got to be another way we can phrase that. Hydrogen hydroxide sounds kind of strange. Let's just call it water, H2O. What you just witnessed is a neutralization reaction. And this is just like a reaction class we saw in the first half of the lecture. Specifically, it's a double replacement. I use a lowercase d and a capital case R. That was kind of silly. But still, it's a double replacement reaction where the HCl and the NaOH swaps their partners to form salt and water. And this is actually a really good thing to know, because we took 2 really powerful substances, hydrochloric acid and sodium hydroxide. We reacted them with each other, and we made a very tame and not dangerous salt and water. You stick your hand in a solution of either of these, and you're going to pull back bones, if they were concentrated enough. But salt and water are very innocuous. There's really important safety ramifications to this. So I've spent, over 10 years working in the lab, and it's bound to happen. You're working with some acids and you get some on your hand. What's a really useful remedy is to apply, a basic solution to that to neutralize the acid before it eats through your skin, So it's a good skill to know that acids and bases are dangerous, but they can be tamed if you have a solution of neutralizer, at hand. We can further categorize acids and bases into 2 rough categories, strong and weak. When we think of, let's start with acids. A strong acid, this is an acid that will completely ionize in water. That's how we define it. It would be something like hydrochloric acid, HCl. If we took 1 mole of HCl and dissolved it in water, we can expect to form 1 mole of hydronium added to the water and 1 mole of chloride, because they would both split the moment they hit the water. Another example would be, you may have heard of this. This is the formula, sulfuric acid, H2SO4. This actually has two protons associated with its partner in the molecule. And it's also a strong acid that you do not want to dip your hand into. Okay, strong acids for the most part, yeah. You can use these as reference points. Weak acids, these partially ionize in solution, okay? And some examples of that would include, acetic acid, which is the acidic portion of vinegar. And that has a structure like this. It's got so this, even though this looks like hydroxide, this H in the OH group, this can dissociate and liberate a positive proton to form hydronium and leave behind a negatively charged on the oxygen. This is acetic acid, vinegar. This is a weak acid. If you were to have a mole of acetic acid in solution, like less than 1 out of 1,000 would dissociate, I believe. That goes to show how weak it is compared to hydrochloric acid and sulfuric acid. All right. Now, on the flip side, bases can also be strong or weak. Examples of strong bases, oops, there's my cursor, include, first row metal hydroxides. Sodium hydroxide, potassium hydroxide, stuff like this. This is lye, and it is quite corrosive. You do not want to touch this. It will burn you and it will hurt. Examples of weak bases, which if a strong base, like a strong acid, would fully dissociate into one equivalent of hydroxide and one equivalent of the counter ion, then a weak base, like a weak acid, is going to partially split. Examples of that include second row. I'm sorry, this should be second group. Second group metal hydroxides. Group. Examples of this would be magnesium hydroxide. This is a laxative. You can drink solutions of this and not die. Calcium hydroxide, which, like magnesium, has 2 hydroxides for every molecule. This is a pickling agent. It's used in food. So you see, these are much more safe than sodium hydroxide and potassium hydroxide, which are lyes, chemical lye. Okay, which are very powerful cleaning agents and bleaching agents. All right, the last thing we're going to talk about is the pH scale, to expand upon the concept of a power of hydrogen, which we mentioned a few slides ago. So we defined neutral pH as the pH where the proton concentration, or the hydronium concentration, equals the concentration of hydroxide. And that happens when it's, 1 times 10 to the minus 7 molar hydronium or hydroxide. Written another way, 0.123456 molar hydronium or hydroxide. This is really annoying to write out. So that's why we use scientific notation, 1 times 10 to the negative 7. But even this is a lot of 1 times 10, 1 times 10. So scientists came up with the pH scale, which is called a logarithmic scale, which means it's all based off exponents of 10. So what we're doing here for the pH scale is we're just focusing not so much on even the negative part, but we're just going to focus on what this number is. So when we say the pH is 7, the power of hydrogen is 7, we mean that it is 7 decimal places out until we get our numerical measurement, until we get the reading of 1 molar, of 0.0000001 molar, all right? So something that would be, you know, 1,000,000 times more concentrated or of hydronium or 1,000,000 times more acidic would be something with a pH of 1, okay? That's because it's 6 orders of magnitude greater. So it would have a concentration. I'm just gonna make like a division here. 1 times 10 to the power of negative 1 molar, which is the same thing as 0.1 molar hydronium. Okay? So this is more acidic. We can see that as the pH goes down, when pH goes down, acidity goes up. An example of something that would be that acidic would be something, you know, close to gastric juice, which is partially hydrochloric acid. It's 1.6 to 1.8, but just to make the numbers nice and even, we're going to pretend it has a pH of 1, okay? So this shows that, you know, as we increase the concentration of hydronium, the pH is going to go down from 7 to 1. And we can run this in the reverse. Let's look at sodium hydroxide. The pH of that, this will be fun to write out, equals 13. That's equal to 1 times 10 to the negative 13 molar hydronium. Excuse me, I was about to say hydroxide. That's not right. Let me erase that. Hydronium. But you may say, well, sodium hydroxide is a base. Why are we talking about the hydronium concentration? It's a hydroxide donor. Remember that hydronium and hydroxides, they're like complements and opposites to each other. So if we have not a lot of sodium, of hydronium in solution, which is going to be 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 molar, 10 to the 13. We are actually going to have 1 times 10 to the negative 1 hydroxide. Scientists just like to focus on everything in terms of acidity rather than acidity or basicity up to a certain point. All right, so this is what the pH scale is. Boil all this down, we are just looking at the exponent term. That's what we're doing, and ignoring everything else and using that to represent how much or how little hydronium is present in the sample. Okay, and when things are acidic, it's going to have very low pH. When things are basic, it's going to have a very high pH. All right, and what that means, said another way, is that when the power of hydrogen is small, we're moving the decimal place over not very far, like this far, only one place. When it's a very big exponent, we're actually moving it over very far, which means it's going to be very small, okay? So the takeaway here, I'll say it again because this I know can be confusing, is that the pH scale is a logarithmic scale where we take the exponents of the hydronium ion concentration and use that to as a shorthand to describe if something is very acidic or if something's very basic. And in general, it happens to fall between 0, 1 to 14, but solutions can certainly have a pH below or above this, even negative, but that's just not something we encounter very often. I do not expect you to memorize the pH scale, but just look at it and you'll be able to rationalize this out and be like, okay, grapefruits are very sour. They're going to have a lower pH, something that is going to be below 7, which is neutral. So that makes sense. And we know that ammonia is, a very bitter compound, and that's going to have a pH that's above 7, neutral, which means that it's going to be very basic. Or at the flip side, if something's very basic, it's a very poor acid. Okay? So I hope that makes sense to you. This might be another one of those slides where you may want to rewind and really, make sure that you've got a good grasp of it. But of course, other than that, I'm always available via email, Zoom appointment, or we can elaborate on this, during lab this week. Have a happy Halloween, everyone, and stay tuned for a little bit because we're also going to discuss the results of the mid-course poll in the next slide.